Many thanks. I want to do just a final audio check. I'm assuming everybody can hear me. Excellent, thank you. So I'm David Forsyth. We're going to do learning, shading, and lighting without ground truth. But first, I'll introduce you to my colleagues. If I can make the slide advance work, that's interesting. Here we go. The University of Illinois has a big old vision group. It's been influential in vision since before I started, which was a very long time ago. I'm kind of the famous old guy. My two colleagues, Derek and Lana, are famous without being old. Alex Schwing is busy getting famous. And then we got new colleagues, Saurabh Gupta, Liang Yan Gui, Shenlong Wang, and Yuzhong Wang. And we interact very enthusiastically. There's all sorts of joint work. I'm going to talk about stuff that mostly I've done on my own, but that's just because that's what I do sometimes. We've got lots of well-known ex-students. Jean-Ponce and I wrote a book about vision. I've written a bunch of other textbooks. We've got a bunch of startups. It's all flourishing and it's great fun. And in fact, computer vision today is just amazing. The discipline is very strong and effective. I want to talk about that for a few minutes, and then I'll get on to the problems that I'm going to talk about today. So if you look at things like citation metrics, which are at best a fairly dodgy measure, but they're kind of fun because they make us look very good indeed. Of the top 5 conferences in computer science, 3 are vision conferences. And as we know, CVPR is more influential than NeurIPS, which is as it should be. And then the other 2 are ICCV and ECCV. That's pretty good going. If you look at publication metrics on Google, to my immense delight, CVPR is right up there with Science, Nature, and the New England Journal of Medicine. So vision is just growing like topsy, and that's a very, very fine thing. Onward and upward. I pinched this picture from The Spectator because I couldn't resist it. And what has made us so tremendously influential, powerful, effective is essentially a straightforward recipe. Everything else is a really important sideshow, but a sideshow. I used to give this recipe in slides some time ago. And the recipe basically says you get a data set, you get some features, you build a classifier, you submit a paper, and you go around until it gets accepted. Now, of course, that recipe is wrong. The real recipe is this, which is you should use a convolutional neural net in place of any other feature construction. I have never found this recipe congenial, which drives a lot of my thinking, but we need to recognize just how valuable this particular line of thought has been to vision. We are really good at solving problems that can be attacked with this recipe. But we have some difficulties. I think there are 4 big difficulties in vision today. One is, what should it do? Another is there are very clear rules of machine learning, which we break pretty much every minute without anything bad happening, meaning that the rules are wrong and we don't know what the right rules are. There's an awful lot of our machinery that doesn't really behave in any fashion that we understand or can control. We can make it do things, but it doesn't mean it doesn't do nasty things as well. And then finally, there are problems where there isn't very much training data. We can't really get a labeled data set and apply a classification or regression recipe. And those kind of problems are the problems I want to talk about today. So why would anyone care about shading? The short answer is shading has the impressive effect of making different images of the same thing look different from each other. So here are 6 really neat pictures from a webcam in Finland. And you can see that the same crane, I'm not quite sure what kind of crane it is, but the same crane, the yellow one over here, looks very different at different times of day. And those changes in appearance as the sun moves make it quite difficult to determine what particular aspects of the picture actually are. So if you look at this top left picture, you'll see what appears to be a dark shadow over here, but you'll notice that it can't really be a dark shadow because as the sun moves and different shadows appear in different places, this doesn't move. It's probably not a shadow. It must be something else. This dark bit is a shadow. This piece of tarmac down here in the bottom right picture has changed its intensity and its contrast with everything else rather substantially. So we have really serious changes. And of course, these changes are going to mess up classifiers and they're going to mess up detectors. So there are two strategies we can adopt to cope, and these are standard strategies. One is I could try and construct a representation of the image that was independent of shading. And we know what to call this representation. It's called an intrinsic image, but constructing them well remains extremely difficult. I'll show you some progress in that direction. The other thing is I could train a method to ignore shading. I'm going to show lots and lots of examples of what shading can do, and then it'll be good at it and I'll be fine. Current evidence suggests that we don't really know what it means to say enough, and we don't have enough right now. So a persistent feature of thinking about the applications of computer vision is there's a ton of stuff that works great in conference papers, but when you try and deploy it, it kind of doesn't hit the degrees of accuracy that you see reported in the papers. And some of that appears to have to do with things not responding well to shading in real images. So I'm going to talk about two overarching questions, which actually mean that I will spend most of my time discussing entirely different ones. The first question is, I think, insertion rendering. So what I'd like to be able to do is cut an object out of one image, put it in another image, and make it look natural. And there are a bunch of reasons you might want to do that. It's kind of a great paradigm for computational photography. It's very nice for users. I cut my granny out of one photograph and I stick her in another photograph, and now I've got a picture of my living room with my granny in it. But I can also use it for training detectors, for generating augmentations, etc. And the other idea is scene relighting. What I'd like to be able to do is take a picture of a scene and generate a picture of that scene in a completely different lighting that looks natural. Again, you can see the attractions for users of computational photography, but again, I could use this for scene augmentations, for training detectors and the like. So these are two attractive things to be able to do. And we have strategies. One standard strategy for thinking about problems like this is inverse graphics. And the strategy looks roughly like you build a big data set of 3D stuff, you've got surface material details, you've got a physically based renderer, you train a renderer, now you train a regression to reconstruct the 3D from the images. Then you relight the scenes by applying a physical render to that reconstruction, and you're happy. I find this recipe unconvincing. I know I'm sort of rather swimming against the tide here, but I really don't find it compelling. There are two really serious objections. One is authoring really good models of what objects look like remains, in fact, very hard. So it's moderately easy to do computer graphics models that look like really good computer graphics models. It's fantastically hard still to produce models that look like real things. And the difficulty seems to be in the interaction with light at a surface, which is much, much more complicated than most models are willing to acknowledge, and estimating the parameters of good material models. I'm not claiming it can't be done. I'm claiming it's very difficult to do, covering all things accurately at large scale. There is, of course, another question which is troubling, which is almost certainly visual agents, people, animals, that sort of thing, didn't get issued on day one with a huge data set of 3D stuff with surface material details to use when they learn to see things. So it's kind of not a great answer to this problem. And I have a mild agenda which says we really do want to have ways of thinking about vision that make inverse graphics superfluous. We don't have them, which is why it's useful, but we should have them. So the alternative strategy is I'm going to just use actual images of the real world and various forms of straightforward statistical model. I want to be able to use images as data without supervision and exploit various models of spatial statistics. And of course, the real question here is, how do you do that? So let's look at insertion rendering. There is an algorithm. It's been around for a long time now. You take an object out of one image and you stick it in another image. There are very real advantages to being able to do this. It's very good for training detectors, and it's good for consumer rendering. And the problem, of course, is it very often doesn't work. There are minor problems to do with point spread functions at boundaries and the like, but the major problem is lighting. So here's a picture from Jean-François Lalonde's paper back in 2007. These were, at the time, really convincing renderings. Most of the people have been inserted. Their scales are right. They even have little shadows at their feet. Everything's hunky-dory. But if you stick people into other scenes, you discover that lighting problems are really serious. So the bright orange fellow sticks out particularly, but the black car is too dark and the shadow on the base of the car is too dark. The whole thing is falling apart because of lighting contradictions. So if I know the geometry and material of the object that is going to be inserted, then the processes for insertion are now highly developed. There's a really well-established literature. There are some samples from it over here. We can get stunning results, or rather we could get stunning results 10 years ago, and things are only getting better. Here's a scene. We happen to bung a computer graphics model of a statue in the scene, and it just looks great. And results have only improved over the last 10 years. If you know what the object is like in 3D and material, you can do a wonderful job. But if you just cut it out of a picture, you don't know that stuff. And we still don't know how to recover really good, really detailed 3D material and surface models from a single image. It remains a painful open problem in computer vision to recover models of this kind of quality. So what we want is, I have a bunch of scenes on the left over here. I'm going to stick a sphere into the scenes, and I know what the sphere looks like because its albedo is the albedo of a circle. So I'm going to bung it in over here. And of course, if I just leave that cut and paste, it'll be ugly. So something happens, and I get the pictures on the right where these spheres actually look like spheres, and they're shaded like spheres, and they participate in the shading to the extent that they look as though they could be there. How would we do this? Well, the key question here is what changes or what doesn't change when an object moves from an image to an image. So we know when I take an object out of one image, its albedo and a bunch of material properties do not change. They're intrinsic to the object. But the shading changes. It's extrinsic. So what we're going to want to be able to do is make the new image have the property that the object I moved has its original albedo and material properties, but its shading has changed and it's consistent. So there is a traditional vision problem here with very special features. How do I take a picture and decompose it into its intrinsic components and its extrinsic components? By the way, it's important to understand that albedo and shading are examples of intrinsic and extrinsic components, but they may not be the right ones. The problem with this problem is there isn't any real training data. It isn't even clear what the right decomposition is. Physics is a rough guide, but it's by no manner of means an accurate guide. And I'm going to claim, and I'll demonstrate, that you can actually learn this problem very well without any ground truth. So how would we use it? There's no point in solving a problem if we don't care about the solution. What we could do is the following. I could take an image of a scene and then an image of the scene with an object placed in it. Now, of course, I just cut and pasted that object, and I'd have a mask. And I'd stick those two into a renderer, and the renderer would do things, and the rendered scene would have to pass a couple of tests. So firstly, it would need to be like an image. We kind of know how to do the like an image test. That's what the wonderful adversarial framework is all about. Then, if I took the rendered scene with the object in it and decomposed it, I know what the albedo should be. It should be the albedo of the background for the background and the albedo of the inserted object for the inserted object. And then I could look at its shading and ask, is that like real? So tests like, is this an image? Is this the cut and paste albedo? Are these like the real? These are tests we know how to do. The problem we have to think about is the image decomposition network. And to do that, we have to learn without the right answer. So there aren't any ground truth decompositions. There never will be. We know that you can render things. It's doable but hard. But there's a strong thread in the modern literature that points out that if you only use renderings and CGI material, you get relatively poor results. You have to do something else as well. That's good reason, to my mind, to be suspicious of rendering. Actual modeling of surface detail is very hard, and measurement is very hard. So we have to train a decomposer without knowing the right answer. And of course, RetNex provides clues. So RetNex is something that appeared before I was born. So it may be unfamiliar to many members of the audience as well. It's an idea due to Edwin Land back in the 50s. So the problems I've posed have been known since the 19th century. But Land basically said people are really good at telling what the albedo of a thing in an image is. How could that be? Here's an answer. Surface color changes either quickly or not at all. So you can think of surface colors appearing in constant patches, which he called a Mondrian. The light color changes slowly. And then what you could do is you start at this red patch. I'm hoping people can see my pointer here, but there's a red patch and there's a path. You move along the path, accumulating the changes. And if the changes are small, you assume that they're due to the light, and so you ignore them. And then you hit a big change when red turns to blue, and you keep that. And then you ignore the small changes. Then you finally hit the point whose albedo you want to estimate, and you use that with you estimate that with an average over paths. Now, it turns out to be quite difficult to come up with a crisp description of what this algorithm actually does, but the answer is based in differentiating and reintegrating the image. So what can we learn from this? Well, what we could learn is you can build rough spatial models of albedo and shading, which are good enough to decompose images. So the hidden, rather nasty secret here is RetNex remains moderately competitive as an intrinsic image algorithm even now. So what I'm going to do is build fake models of albedo and shading and use those to make fake images. And I can use those to train a method. And of course, there are various options for albedo and shading. I'm displaying here some of the Mondrian style models of albedo on the top row. Then there's this computer graphics albedo model in row 3, a couple of shading models in rows 4, 5, and 6. And then the final is a computer graphics shading model. So what we're going to do is build an albedo paradigm that captures the idea that albedo is a piecewise constant, that has a reasonable distribution of colors, has many edges, no orientation bias, and some vertices with high degree. We'll build shading models that are mostly smooth, but with sharp edges, that have dark and light spots and uniform color. And these models, the way we'll work with these models is we'll just draw samples from a spatial model. How did I get the spatial model? Experience and guessing, but as we'll see, it doesn't seem to matter very much. And now what I'm going to do is train a regression network with these models. So if I give them a product of one of my fake shadings with one of my fake albedos, I call the fakes paradigms because I've got to call them something, then I know what it should do. So I can take a paradigm image, feed it in, and decompose that into an albedo and a shading, and I know what the right answer is. The problem, of course, is if I just train it like that, it's going to do strange things on real images, and I don't want that. So I'm going to have to feed in real images, and I'm going to have to prevent it from doing strange things on real images, and that'll take some thinking. So we have some easy losses. If I stick in a paradigm image, I know what the albedo and the shading should be. And if I stick in a real image, I know that whatever albedo and shading I should make, I make should be like the image when I multiply them. I can't just randomly pull albedo and shading out of the air. Now, the second thing I know is albedos are like paradigm albedos. Why? Because I'm using the paradigm as a model of albedo, and shading is like paradigm shading. So I expect that if I stick some image into the decomposer and I get an albedo and a shading, I can stick those albedos and shadings into an adversary that is trained with paradigm albedo and shading. And I'll do this, I'll test this only locally using a patch-GAN-like trick. Now, the thing about this is it's not really amenable to GAN-style analysis. There is no reason to believe that the saddle point or the mythological saddle point that appears in so many GAN papers but cannot be shown to exist is actually there. In this case, there's very good reason to believe that it isn't there. So the best we can do is say it's a smoother. I'm going to adjust the adversary to complain whenever my decomposition doesn't look like a paradigm. I'm going to adjust the network output to fool the adversary, and that should help. As a result of GAN theory not applying, there's no reason to believe that distributions can match. There isn't a saddle point. This isn't really a loss. It doesn't really converge. And the main consequence of that is if you stop the training at different points, you're going to get different albedos, which is really annoying. So I'm showing you here an image that went in. I stopped at one point and I got this rather nasty pink stuff. I stopped at another point and I got less of the pink stuff, but there are other problems. We need an equivariance property, and this equivariance property actually should extend to space as well. So the first thing we want as an equivariance property is the choice of models shouldn't change the answer. The second thing we want as an equivariance property is if I translate or rotate or scale the image, the albedo for the translated whatever image should be the translated albedo. Why? Because albedo actually has that property. The shading should be the translated shading. Why? Again, shading actually has that property. The first thing I want to notice here is equivariance doesn't come for free. Regression networks don't a fortiori or a priori know that they need to be equivariant. And you can demonstrate that easily. So here's an image. What I did was I cropped out the top left corner and I computed its albedo. Then I cropped out the bottom right corner and I computed its albedo. And you'll notice that the bits where these overlap, somewhere around the kittens, the top left has all this nasty pink stuff and the bottom right does not. The network does not know that what it's supposed to produce should be equivariant to cropping. So how could we impose this? There are two things you could try to do. One is you could try to come up with some scheme to impose it during training. I have tried unsuccessfully a variety of such schemes. I'm not talking about them because they didn't work. I don't know why they didn't work, and somebody might come up with one that does work, and that would be a very good thing. But assuming that that isn't there, here is an alternative. I can take a moving average of model coefficients, and that smooths across adversarial models. So the thing is now equivariant to choice of models because it's an average of all available models. For translation, what I'm going to do is cover the image with many shifted overlapping tiles on a random pitch, and there's some weighting and stuff that you have to worry about to get things right. And then for each tile, I'll recover albedo and shading. The albedo at a pixel will be the weighted average of all the overlapping tiles. The shading at a pixel will be a weighted average. And then, of course, for scale, I'll rescale up and down, and then I'll recover using translation averaging at all scales, and then rescale back and average the results. And for rotation, I will average those estimates over 8 flips. Yes, this is very expensive. It makes a big difference. Averaging is extremely helpful. So over here, I'm showing an image, and then below are top left and bottom right. They're showing all sorts of ugly effects. And these ugly effects are essentially estimation errors that occur in the network's coordinate system rather than in the world coordinate system. So if you move the image around and pass the network in, they will tend to average out. When they do, they produce albedos that are really very good. This is the best albedo. Why is it helpful? There are two ways of thinking about this. One is I'm making an ensemble estimate of albedo at each point, which is an ensemble over scales and translations and flips, and that must reduce the variance of the estimate. Another way to think about it is the adversary and the network can't control some kinds of long scale error that are keyed to the tile coordinate system rather than the world coordinate system. And if you randomly crop to tiles and scales, what you're doing is essentially suppressing this error by averaging. So the averages are estimates at different locations, and that causes this error largely to go away. The nice thing about all this is you can evaluate it, and there's an evaluation framework due to Sean Bell, Kavita Bala, and Snavely back in 2014. And the idea is I go out, they went out, collected a bunch of images and asked people to say, is this one lighter than that one, using surface lightness as a property. So is one lighter than two? Is one darker than two? Are they the same? Then what you have to do is match the human judgments according to weights. And that gives an evaluation task called WHDR. It's the weighted human disagreement ratio. Now, there are all sorts of issues with WHDR. There are entirely reasonable objections to it, but you can evaluate and people can compete, and that's usually a good thing. So what do we get? Well, basically what I have shown you gets a test WHDR under standard conditions of 16.86 without ever having seen any IIW data. So the pink ones at the top are a whole bunch of competitive methods. You'll notice RetNex is really pretty good, 18.69 WHDR, smaller is better. These are a whole bunch of competitive methods that do not get to see IIW data. If you get to see IIW training data during training, you can get a better WHDR, but not a whole hell of a lot better and with consequences, as we shall see. So what I described may look a little shaky, but it gets a very good WHDR. The qualitative results are very nice. So, you know, it takes quite a lot of practice to actually evaluate them. I like these. You can see that really complex shading and specular effects in this photograph of a bath have just been squished, and the thing knows, look, these are white tiles with a silver thing. That's very pleasing. A lot of fine scale shading effects on this man's jersey have been suppressed, and that's very pleasing. Most of the fine scale shading effects, but not all, on this bed have been suppressed, and that is very pleasing. And big indoor shadow things get suppressed. A lot, but not all, of deep shadow gets suppressed. You can see specular effects here that made it through, but there are quite a lot of somewhat less significant gloss effects that get suppressed. That's fine. But WHDR is tricky. So you should notice this is the state-of-the-art WHDR of 14.75%. I should have replaced that hours, but it's in the table. And you will notice that the albedos these methods with really good WHDRs produce are extremely odd. The reds are very pronounced, the colors are a bit strange, and they're very flat. There's a sort of colored paper effect. What that means is it may be very difficult to use this albedo either for detection or for multiplying by a shading field to cover another reconstruction of to produce a different shading of the scene. Why? Because they suppress details that are kind of important. Here are more examples of this indecision and colored paper effect. It affects everybody, by the way. We get it too. So here is an image. Here is its albedo. And you can see down here, the thing has decided that this lens flare or the specular flare on the table is a problem, but it's not a problem that it's completely willing to solve. It's put some of the flare into shading and some of the flare into albedo and crossed its finger. I refer to that as indecision. There is a tendency in competitive methods. So the top row shows a very strong method due to B et al. From 2018. There is a tendency to suppress shading details that are actually intrinsic rather than extrinsic. So if you look at the little edges of these shelves in the cupboard, that effect is intrinsic because however you light the scene, you're going to see it. Why? Because you can't get light in there. It's a narrow groove. Reporting it as mostly an extrinsic phenomenon means that when you render this with another shading field, the shelves will not have little shadows underneath them, and that's a nuisance. Now, so we got to go to some sort of numbers because this is a scientific talk and scientific talks have numbers in them. These box plots are kind of complicated, but reading them is, once you're used to it, is easy, and they convey quite a lot of information. So the nice thing about a method that sees absolutely no IIW data in training is you can use simulated test sets as well as the standard test set. So imagine on the left, I use a strong version of one of my models. Then on the standard test set, I'm getting in the early 17s as a WHDR. This is not the very best, it's a strong version. If I leave out that adversarial smoothing I described, remember it doesn't submit to any GAN theory, it's a little bit shaky at best, but it seems to be very helpful. I get a much higher WHDR. It's almost the same as Liu 2020's WHDR and heading towards RetNex. And if I leave out the paradigms, the fake images, and just use the adversarial smoothing, it gets worse. Now, the next thing to compare over here is these simulated test sets. So what I'm going to do is draw 500 test sets, the same size as the original test set, at random using replacement. So these are bootstrap draws, and then apply a fixed threshold to those test sets. And I'll look at how they perform with a box plot. So you'll notice several things. First is that the standard test set is easier than the average simulated test set. Most simulated ones get worse WHDRs, but nonetheless, using a fixed threshold on a simulated test set, the strong model seriously beats adversarial smoothing, a model without adversarial smoothing, and it seriously beats a model without direct paradigms. Now, the next question you've got to ask is, what about all that equivariance and averaging and stuff? Does that make any difference? And the short answer is we have three things we can compare. One is the standard test sets. And if you look at the standard test set with averaging on a strong model, I'm going to get about a 17 WHDR. And I leave out the averaging, I get this blue bar, which is about a 19 WHDR. So I'm getting 2 points in WHDR just by averaging. And that applies as well with the simulated test sets. So these green are typical for simulated test sets with averaging, and the purple is the typical without. That equivariant averaging really matters. It's not just a property of albedo, it's a property you need to impose to be able to estimate. There are some other neat things that follow from these numbers. So the scale at which you apply a patch-GAN adversary is important. I can have my adversary look at the image at very short scales. So on the left, you can see a 128 by 128 tile and a representation of what that scale looks like. It's a very, very small tile. It's a 10 by 10 tile. Then there's a 22 by 22 and so on. If I look at a very small scale, the model works badly. Why? Because knowing what albedo and shading look like at a very small scale just isn't very helpful. As the scale gets bigger, the model improves. So somewhere in about 22 pixels in 128, you get a much better model. And then as the scale gets bigger still, the model fails. Why? Because my albedo paradigms, my fake albedos, aren't anything remotely like real albedos at a long scale. My fake shadings aren't even remotely like real shadings at a long scale. But choosing the right scale is very advantageous. Computer graphics is a problem. So what we're going to do here is compare training with various bits and pieces of CGI paradigm against albedo paradigm. So in the green bar, I'm using colors in a propagandistic sort of way. Green is good, red is you should be worried, and so on. In the green bar, I'm using my fake albedos and my fake shadings, and I get a very good WHDR. If I simply replace those with CGI albedos and CGI shadings, I pay a huge WHDR penalty. Now, this penalty is known but not understood. The literature is full of references to the fact that you can't just train on CGI albedo and shading for an intrinsic image method to work. If I use my fake albedo and CGI shading, the penalty is a little bit smaller. It got worse, but not quite as much worse. If I use my CGI albedo and my fake paradigm shading, things are much better. And if I use a simplified albedo of mine and a paradigm shading, they're better still. This suggests gently that the main problem is in the CGI shading, and that a secondary problem is also in the albedo. And by looking at the images, we can sort of get a sense of what the problem is. So here are my paradigm albedos, and this is the simplified, and here's the CGI albedo. And you'll notice that the CGI albedo doesn't have much spatial action. The paradigm albedo is changing all over the place, the CGI doesn't. If you look at the CGI shading, you will notice a persistent nuisance, which I'll zoom in on here. So CGI shading is generated with physically realistic renderers. physically realistic renderers always generate render noise. That render noise is usually too small for anyone to perceive it, but it's there. And that render noise appears to be occupying whatever goes on inside the network in an unfortunate way. So the shading noise appears to be a problem, and the shading is too simple compared with my shading model. So what is going on here? My spatial models, these paradigms, are basically very aggressive summaries of real problems that leave out stuff that isn't particularly helpful. So large constant areas of albedo, say, are not particularly helpful for learning. What you really want is constant changes. So paradigms pack more problems per pixel is the alliterative slogan for this. So let's go back to our finished webcam. Here is the finished webcam changing with time of day. Here's what the shading fields look like, which is pretty promising. But here's what the albedo fields look like. And it's worth noticing that intrinsic images, which have been open for 150 years, are not closed, right? There's a whole bunch of stuff here that is changing and should not. If this method was absolutely right, all of these pictures would be the same, and different pixels would have different values. One of the major problems is something I call indecisiveness. So I have not been able to get rid of this. It's a problem in all modern intrinsic image methods and in RetNex and the old ones as well. If you take an image with a deep shadow in it, the method likes to produce an albedo with a bit of shadow in it and a shading with a bit of shadow in it. And as far as I can tell, this has something to do with averaging in regression losses, but it's a good problem to solve. Okay, I want to go back to insertion rendering. So I described a procedure. I said, look, what I'm going to do is beat the picture up so that it produces albedos that make sense with the cut and paste albedos and shadings that make sense. I showed this diagram of how it would work, and lo and behold, I can do insertion rendering. Here's a cut and paste image. A sphere has been inserted, you know, because there's a white circle for its albedo. If you harmonize the image of the inserted object, you'll get something that sort of looks like this. It changes the color of the sphere. Our method produces something that looks like that, and a real scene, a real photograph, looks like this. So we can get comparisons that are reasonable. We do get quite nice behavior in dark environments, but we don't get shafts of light. So up here, you'd like to see a shaft of light on the car from these shafts, and that's just not there yet. Whoops, we'll leave that out. One of the more interesting features is if you insert spheres into images, you'll discover that they seem to have shading that is consistent with a single shape. So what I can do is take some of these spheres, compute a 3D reconstruction of the sphere from the shadings, and then compare it to a reconstruction of the other spheres, or reshade it and compare it to the other spheres. And when you do that, you discover that this thing has some kind of emergent theory of shape. All of these spheres have the same recovered shape, and that isn't something it was taught to do. Okay, so let's get to relighting scenes. So I've shown that we can do some things about insertion rendering. I want to talk about relighting scenes. Now, it should be relatively straightforward. I want the following shading. I'm going to multiply the albedo by the shading, and I'm going to go home early. And of course, that doesn't work. So a couple of albedos over here, multiplied by desired shading, they look horrid. And the reason they look horrid is that shading is very, very tightly correlated to albedo. Why? Because albedo is going to tell you things like where two objects meet. It's going to tell you about contacts. It's going to tell you about corners, and shading is funny in those places. So shading and albedo are very highly correlated. What could we do? Well, what I would like to be able to do is know what shadings are available for a particular scene. And there is an old idea in the literature, the Illumination Cone, due to Kriegman and Bellumer back in '98, which says all the different lightings of a scene form a convex cone. So there's an easy case. Imagine I have a bunch of pictures of a scene with one light on and all the others off. Each picture is a generator of a cone. Any non-negative combination of those pictures is a legitimate picture. So I've got a convex cone. What I would like to be able to do is impute the n generators of this cone from individual single unlabeled images of scenes. Now that should strike you as being a bit difficult. Kriegman and Bellumer show that you can get really good cones by basically taking pictures with one light on and all the others off. But what I want to do is just take a picture of a scene and then figure out the cone from that picture. How could we do that? Well, there's about 40 years of illumination physics and rendering theory rides to the rescue. And there's a key idea. Images of similar scenes with similar luminaires, similar geometry, and similar albedo will actually have similar cones. It is easy to prove this in the case of similar luminaires, harder in the case of similar albedos, and very hard and entirely novel in the case of similar geometries. But you can get a bound, and the bound tells me the radiosity of these scenes, and so the cones are going to be really quite similar if the geometry, albedo, and luminaire are similar. Now, what that means is if I have a scene and I can figure out other scenes that are similar, I know they have the same cone. I also know that the luminaires are at slightly different intensities, meaning that I see slightly different combinations of the generators. In turn, I should be able to recover the generators from that data with a little extrapolation and smoothing. And there's some easy losses. The imputed generators that I recover should be different from one another, and that's a log det loss. The shading of the image and its neighbors should be within the cone, as should, and you can do that using residual losses. And then there's some hard losses. The generator, any generator times the albedo should be a real image, but there's an extrapolation problem here because you do not see extreme lightings of real images in typical data sets. So it's a real image, but it's an unusual real image. And a relight using a generator should be like a real relight. So my generators are extreme lighting conditions and the real images aren't. So I can't just sling an adversary in and go home early. The current solution is the local adversary is a patch-GAN-like adversary, which compares to images that have been multiplied by some constant, allowing very bright and very dark patches. And that seems to help. Okay, the real relights, changes to relighted images should look like relights. So if I take an image and then I relight it, that should look like a relight. I should have changes in shading, but not in albedo. Now, the problem here is I don't have any relights, but I do have paradigms. So what I can say is real image and relighted image should be like paradigm albedo 1 times paradigm shading at 1 and paradigm albedo 1 times paradigm shading 2. That gives me an adversary I can run at a patch-GAN scale, and we can use that. Okay, how do we evaluate? There are two distinct questions here. One is the relighted image realistic? Now, I could do really well on that question by simply reporting the original image, so that's not quite the only question. And the second one is it different from the original? So realism is easy to test because it should remain a real image, which means if I have a big pool of bedroom images and I relight them all, then that should be the same as a real big pool of bedrooms, meaning the FID between the relighted bedrooms and the original bedrooms should be 0. Now, of course, it isn't going to be 0, and FID has a 1/n bias, which nobody seems to know about and is extremely important in comparing methods. If you want to know the details, it's kind of a second-year stat grad student class exercise. If you want to know the details, it's in a CVPR paper that I did with Minjin Chung. And that measure is easily fixed. There's an FID infinity, which is unbiased in that respect. And then, of course, I can measure diversity by looking at the RMS pixel value difference between the image and the relighted. Now, of course, what I could do is rescale them both so that this diversity was as big as I liked. So what I'm going to do is scale the relighted image so that its mean intensity is the same as the original image. That gives me some sort of scale, fixing of scale. And what we see when we look at methods looks roughly like this. I can get FIDs that run between the 4s and the 16s, or FID infinities between the 4 and the 16s. The numbers are about the same, it's just they're unbiased. And I can get per pixel RMS differences, that per pixel per channel RMS differences that look like somewhere between 0.1 and 0.2, meaning about 10% to 20% of full scale. Of course, where I want to be is in the bottom right corner of this graph, and it's difficult to get there. You'll notice that the methods tend to cluster along a line. So what do they look like? Okay, I have an image over here, and then the first row is the first 5 generators, which have been multiplied by the albedo. And the second row is the second 5 generators. And you'll see that these look like distinct lightings of that scene. They don't look as though they cover every available lighting, not that shocking, but they have some nice features. So for example, here is the image, and you will notice a pair of cast shadows cast by the sofa and the corner of the window. One of these generators has very little of those shadows. It knows that it's supposed to suppress them. Another generator prominently presents those shadows. Here's another scene. Here on the wall are flares from small lights that are hidden behind the screen. In one generator, those lights have been suppressed, and you'll see that the flares, the method is attempting to suppress the flares as well, and it knows that if these lights are dark, then this side of the room should be dark. In another generator, what it's doing is it's saying, okay, you can have a bright wall over here, but all the light from the ceiling that is illuminating the floor has gone dark. Here's another scene with a set of selected generators that should look good. There's directional lighting coming in from the window. Down over here, that directional lighting is heading in a slightly different direction, causing these patches between the structural members to be dark. Here, what's happened is that lighting is much more diffuse. The window is not as bright, and as a result, the cast shadows are not as strong. Of course, it runs mad on occasion. So whatever happened here is difficult to explain, and one doesn't want it to happen. And we can get some sense of what's going on. The extent to which you want to force the method to produce very different images is the extent to which it occasionally panics. So here are a set of generators on the bottom that look pretty good, and they've got lower FID from a method that produces relatively tame relights. Here's something that really sticks its neck out and produces wild relights. I'm getting, almost 0.3 in difference. And of course, it gets some images very badly wrong. I'm a couple of minutes over, so I'll skip that one. Evaluation, the main point here is the evaluation remains very hard. So open questions. I think CGI should be considered harmful for intrinsic images. This isn't news. There's considerable support in the literature for this position. Then the question comes, when is CGI useful? I think the answer should probably be, it's always dangerous because at least surface models aren't exact, and spatial noise in physically based rendering distracts networks. That doesn't mean don't do it, but it means it's dangerous and you need to take on those risks fairly carefully. When is it a distraction? And the answer, I think, may be often, because you may find yourself solving problems that don't exist. The cues to the kind of things we want to know about the world are clearly there in actual images. Why? Because the creatures that see do not see because they got issued with CGI. There needs to be a good reason not to exploit those cues. And there are good reasons, efficiency, cost, that sort of thing. But simply using CGI and ignoring the fact that the cues are there is dangerous intellectually. We are missing things that we need to know. More open questions. So I used spatial models, fake data, paradigms. Question, what can we learn with just images and spatial models? How do we know what spatial models to use where? I pulled those out of my ear based on a tradition of about 70 years of study of albedo and shading, but that particular resource may not be available for every problem. How do we exploit this paradigms as aggressive summaries idea to come up with more effective training data? Remember that when you augment images to train classifiers, you're not looking for augmentations that are realistic. You're looking for augmentations that improve behavior, and tradition suggests that they're very different ideas. So in the question of reshading, we need better, or relighting. and reshading. We need better evaluation metrics. So FID doesn't really make sense here because not per image. Comparison to ground truth is practically hard and may not be helpful. And human subject evaluations are clunky. It's a big question here. When is a picture realistic enough? Finally, in relighting, the method I showed you obviously knows stuff about geometry, normals, depth, whatever. How do you get it out without just using labeled data? That method incorporates some physics, but not much. What kind of physical model is required and helpful to advance a relighting agenda or any other agenda? And can we do data augmentations like this? By the way, there's a little bit of sort of background evidence of success here. I don't want to talk about it in detail because it's a bit shaky, but watch this space. It seems like we can. Okay, my key points. I'm 5 minutes over, which for me is very shocking. I try to run to time, but there you are, you see. Vision is flourishing. It isn't just classification and regression or regression using pictures. Shading and intrinsic images really matter. There are lots of applications, and I hinted that an intrinsic image wasn't just an albedo and an extrinsic image wasn't just shading. And then I argued you can learn very well without ground truth. I showed you SOTA intrinsic image decompositions without any training data. I showed you SOTA insertion rendering without any training data. And I showed you SOTA scene relighting without any training data. I'm going to show you a lanyap because it's just fun to end on a fun thing. So it is nice to turn faces into cartoons. There's a big literature on turning faces into cartoons. The expression of the cartoon should be controlled by a face, and the style should be controlled by a random number. If you do it well enough, you could do this to a video. So what we're going to do here, or the video I'm going to show you, every single frame has been adjusted separately, right, by a random number. There is no training for temporal coherence or anything else, and we'll have a little fun. So she should, every time the random number changes, so does her hair color and her hairstyle and all this stuff. Why did I show that? Because it's fun, and here are my key points, and I'm done for the day. 7 minutes over, I apologize.